All right, so this is the last part of the recording for 2.6 part 2. This is section 2.6 part 3. So when we last left off, I did not do C. So let's look at C together. We have the limit as x is approaching negative infinity. And when we plug that in, we get 3e to the negative infinity over e to the negative infinity minus 4. Now, if you remember from the rules, e to the negative infinity is 0. So I get 3 times 0 over 0 minus 4. So what I get is 0 over negative 4, which is 0. So the answer to this one is 0. Okay? So once again, remember e to the negative infinity is infinity, and e to the negative infinity equals 0. Okay? When we're talking about limits. All right, so for example 8, this is kind of winding everything together, trying to figure out, hey, what do we do with this? So it says, example 8, find the domain, intercepts, and use limits to find any vertical asymptotes, holes, and end behavior. So why don't we look at this and look at the horizontal asymptotes first, see if there's that or the oblique asymptotes. So if I look at this, I see that the numerator's highest power equals the denominator's highest power. So when that happens, I can just look at the coefficient, which we have 1 over 1, because it's 1x squared over 1x squared. So I know we have a horizontal asymptote where y equals 1. Okay? Now let's look at the vertical asymptotes and see if we have anything dealing with that. So when we do vertical asymptotes, it's best to factor things out. So if I take an x, the GCF of x out of the numerator, I get x plus 3, and the denominator factors into x plus 3 times x minus 2. Okay? When I look at this, I see that the x minus 3's cancel each other, so that tells me that I have a hole. When that happens, when the binomials cancel each other, you get a hole when this equals 0. So we know that x equals negative 3. There's a hole there. Okay? And I'm looking at it, so I have now x over x minus 2 left over. So I know that there's a vertical asymptote when x equals 2. Okay? So I know I have a hole. I also have a vertical asymptote. Now it's asking me for intercepts. So this says that y equals, we're going to leave this as x over x minus 2 to solve it a little bit easier. So for the x-intercept, you let y equal 0. So I get 0 equals x over x minus 2. If I multiply both sides by x minus 2, this happens. So I get 0 equals x. Okay, so that point's 0, 0. And then for the y-intercept, we got to let x equal 0. So I get y equals 0 over 0 minus 2. So 0 over negative 2 is 0. So that coordinate 0, 0 as well. Okay, and then it says, check out the end behavior. Well, we already know because we have a horizontal asymptote that y equals 1. But if you really want to check, you take the limit as x is approaching infinity. And then we're also going to take the limit as x is approaching negative infinity of x squared plus 3x over x squared plus x minus 6, right? So once again, dividing the highest power in the denominator by each term. I get this. And now when I do the math, I get 1 plus 3 over x over 1 plus 1 over x minus 6 over x squared. Now remember, we're plugging in infinity. So when we plug in infinity, this goes to 0 and these two go to 0. So I get 1 over 1. So the end behavior, as x is approaching infinity, it's going to be 1. Okay? So what I'm going to do is I'm going to use that little formula we just found. We're going to plug in negative infinity and see what happens. I'm going to have to do this on the next page. So we're going to, whoa. So we're going to take the limit, and let me change the color of this because I kind of want it to be white. So you guys hold on for 2 seconds. Okay, there we go. Let's try that because it looks bad. All right, so the limit as x is approaching negative infinity. Remember, we got this down to 1 plus 3 over x over 1 plus 1 over x minus 6 over x squared, right? So once again, we're plugging in negative infinity. And remember that 3 over x is going to go to 0 because you have 1 over, or 3 over a very, very large number. 1 over x is going to go to 0, and 6 over x squared is going to go to 0. So if I go x approaching negative infinity, I get 1 over 1, which equals 1, okay? So if I put all those pieces together, the horizontal asymptote, the holes, the vertical asymptote, let's see what this graph looks like. Okay. So if you look at your work, I'm going to go out 4 units in each direction just so we can see what's going on. Okay. All right. So when we did this, we found out there was a horizontal asymptote where y equals 1. So I'm going to go ahead and put that line in. There's my horizontal asymptote line. And I also know that we had a vertical asymptote where x equaled 2. So I'm putting that line in. The other information, I knew that there was a hole when x equaled negative 3. So to find that, I'm going to have to find the y value, so I'm just going to skip it for now. So if I look at that, I also know that the end behavior, the limit as x is approaching infinity, it's going to go to 1. So I know my graph is doing something like this, right? And because we have the horizontal and vertical, I know my graph has to shoot up like this, okay? And then as x is approaching negative infinity, I know it's going to 1, so I'm going to go ahead and draw that in. And then I know this graph is going to do this because of the limitations. Now, remember we have a hole when x equals negative 3. So I'm going to go ahead and put that hole in there. So my graph is going to look like this. So you can use this information that we just learned to kind of help you graph. And it makes it much easier and faster. So that's the answer for example number 8. Okay, this is example 8b. I'm on page 22, even though I didn't take a picture of the actual notes. But example 8b says we have f of x equals 3x squared plus x over x minus 1. And it tells us to do the same thing. We have to find any vertical asymptotes, intercepts, holes, that kind of thing, end behavior. So if I look at this, I'm going to look at to see if there's horizontal asymptote or an oblique asymptote. So if I check this out, I notice that the numerator is greater in terms of the highest power than the denominator. So when that happens, we know we have an oblique asymptote. So I have to use long division to find out what that oblique asymptote is. So I get x minus 1 going into 3x squared plus x plus 0. So 3x squared divided by x is 3x. 3x times x is 3x squared. 3x times a negative 1 is negative 3x. And then I change my signs. So I get 4x plus 0. And now 4x divided by x is 4. 4 times x is 4x. 4 times negative 1 is negative 4. Changing up my signs, I have a remainder of 4. So this is plus 4 over x minus 1. So my oblique asymptote is y equals 3x plus 4, okay? While we're on it, let's go ahead and do the end behavior because that should be really easy to plug in. So remember, when you have an oblique asymptote, if I plug in when x goes to an infinity or negative infinity, as it stands, I get infinity over infinity if I just plug it in. So remember, we use the oblique asymptotes equation to plug in. So I'm going to actually take the limit as x is approaching infinity of 3x plus 4. And this should be plus 4 over x minus 1. So if I plug in infinity, I get 3 times infinity plus 4 over infinity minus 1. We know that 4 over infinity minus 1 goes to 0. So I have infinity plus 4. So the limit as x is approaching infinity equals infinity. Okay? So we know that. If we do the same thing with negative infinity, if I plug it into the original equation, I'm going to get infinity over infinity, which is indeterminate. So I have to use the equation that we came up with the oblique asymptote. So I'm going to plug that in. 3 times negative infinity plus 4 over negative infinity minus 1. This goes to 0. This goes to infinity. So I get infinity negative plus 4, still going to be negative infinity. So I have the end behavior done, and I know there is an oblique asymptote. The only thing left that I have to do now is see if I have a vertical asymptote or a hole. So if I factor out the numerator, I get x times 3x plus 1 over x minus 1. So nothing crosses out, so I know I do not have a hole. But in the denominator, I see I have x minus 1. So therefore, my vertical asymptote is x equals 1. Okay? So what I'm going to do is I'm going to go ahead and I'm going to draw out the vertical asymptote, the oblique asymptote, and then we know the end behavior. So let's go ahead and do that over here. Okay, so we know we got a vertical asymptote when x equals 1. So I'm going to go ahead and put that in there. And then we have an oblique asymptote. So it crosses the y-axis at 4. Okay, so it has a positive slope. So I'm going to go ahead and put the dot here. This is 1, 2, 3, 4, right? And then I'm going to go up 3 and over 1. So 1, 2, 3 over the right 1. So there's my line. So let me go ahead and place that in there. So guys, I'm going to have to erase this stuff up here just because I'm running out of room. So I'm going to do that. Okay. So that's the information I have for the oblique asymptote and the vertical asymptote, okay? Now I know the end behavior. As x is approaching infinity, it's infinity, right? So we know it's going up like this. Because of the restriction, my graph's going to look like that. Maybe not so rough, but this. Okay? And then we know the end behavior for x is approaching negative infinity. It's going down to negative infinity. So what's going to happen is these lines are going to control the graph. So here's what my graph looks like. It's kind of funky, but it's this. Okay, so there you go. And we have one more problem, and then we're done with this section. I'm going to skip example number 9 so you guys can put a big X through it. But I am going to do example 10. So example 10 says the length of an animal in millimeters t days after birth is modeled by the equation L at t equals 300 over 1 plus 9e raised to the negative t. What is the length at birth and what's the length, or what is the eventual length? Okay. So part A, if t is days after birth, at birth t is going to equal 0, right? So what we're going to actually do is find the limit as t is approaching 0 of 300, 1 plus 9e to the negative t. Okay? So what I'm going to do is I'm going to plug in t equals 0. So 300 over 1 plus 9e to the negative 0 or 0. And if you remember from algebra, e to the 0 equals 1. So I get 300 over 1 plus 9 times 1. So this becomes 300 over 10. 300 divided by 10 is 30. So 30 millimeters is the length at birth of whatever animal this is. Okay, for part B, what is the eventual length? Well, I don't know how long the animal is going to live because it didn't tell me that. So we can make t approaching infinity. Okay, so I'm going to take the limit as t approaches infinity of 300 over 1 plus 9 e to the negative t. Okay, and then we're just going to plug it in. So we get 300 over 1 plus 9 e to the negative, and I'm going to plug in infinity. Okay, so I get 300 over 1 plus 9. I know e to the negative infinity, if you remember, is 0, right? So this becomes 0. So I get 300, 1 plus 0 in the denominator. So 300 divided by 1 is 300. So the answer to this is going to be 300 millimeters. And that is the end of section 2.6, part 3. All right. So the next thing you're going to need to do is upload your notes onto Canvas, and that's a go.